Imagine for a moment that the most powerful intelligent systems on the planet are currently learning about our world, like, well, like feral children in the wild.
Right. There are no carefully curated textbooks for them.
Exactly. There are no patient teachers, pointing at flashcards and saying, this is a cat or this is a dog.
And definitely no red pen correcting their mistakes.
Yeah. They are just dropped into the absolute chaos of human information and basically forced to figure out the underlying structure of reality entirely on their own.
It really is a profound shift in how we think about machine intelligence. I mean, you're talking about algorithms that have to deduce the rules of the universe just by staring at the noise long enough until eventually a pattern emerges.
And that brings us to our mission today. Welcome to the Deep Dive. We are exploring a stack of source material today that details the architecture and the math of unsupervised learning.
Which is such a fascinating topic.
It totally is. And if you are the kind of person who loves grasping complex concepts fundamentally, like not just knowing what these systems do, but how they actually do it, consider this your masterclass. We're going to unpack how machines organize chaos without any human hand-holding.
Because in the modern era of AI, this ability to learn without a supervisor, it isn't just a neat trick anymore. It's the core engine driving the entire frontier of the field.
Absolutely.
But, to ground this exploration, we really need to establish where this sits on the spectrum of machine learning. The sources define unsupervised learning as algorithms learning patterns exclusively from unlabeled data.
Right, exclusively.
But it's vital to note that this isn't like a strict binary. We see a whole gradient of supervision today. There's weak supervision, semi-supervision, where maybe a microscopic fraction of the data has human tags.
And self-supervised learning, right? Which a lot of researchers argue is just a really sophisticated subset of unsupervised methods.
Exactly. But the driving philosophy remains constant. We live in a world of absolute information overload. We simply do not have the human capital to hand-label the entire universe of data. The machines just have to learn to navigate the dark on their own.
Okay, so let's unpack this, because to understand the mechanics of how an algorithm learns on its own, we first have to look at the raw material it's digesting.
Right.
The data itself.
Yeah. And the source material draws a really sharp architectural contrast here. In traditional supervised learning, you rely on datasets like ImageNet 1000.
Right, which is highly sanitized.
It's a manually constructed environment. Human beings sat down and meticulously tagged millions of images, like studying with flashcards where the answers are right there in the back.
It's just an incredibly brittle and expensive way to train a system. You're inherently bottlenecked by human labor and, honestly, human categorization biases.
Totally. But unsupervised data bypasses that bottleneck entirely. The text describes this data as being harvested cheaply in the wild.
Yes, massive indiscriminate web crawling, like the Common Crawl dataset. It just scoops up billions of pages of text, raw code, unstructured data, with only the barest minimum of filtering. It's like being dropped into a foreign city and having to figure out the language and the street layout entirely by observing patterns.
It is, but, and this is key, throwing a machine into that wild ocean of data is useless without the right mathematical survival tools.
Right, it would just drown.
Exactly. The machine needs specific algorithms designed to extract signal from that deafening noise. The text points to foundational techniques like principal component analysis, or PCA, and autoencoders.
Okay, let's break down the mechanics of that, because dimensionality reduction sounds super abstract, but the way I read it, it's like the machine is actively compressing reality to find its essential, structural, load-bearing pillars.
That's a great way to put it.
It looks at a data set with thousands of overlapping variables and mathematically projects them down to a smaller set of completely uncorrelated variables, the principal components.
Yeah, it basically strips away the redundant noise until only the fundamental shape of the data remains.
Which is just wild to think about.
And that is precisely how PCA operates. It calculates the axis of highest variance in the data, like the direction where the data spreads out the most, and defines that as the most important feature.
And autoencoders do something similar, right? But through neural network architectures.
Right. They take a massive high-dimensional input, force it through a tiny mathematical bottleneck in the middle of the network, and then try to reconstruct the original input on the other side.
So to successfully pass through that bottleneck,
The network is forced to drop the noise. It has to memorize only the deep invariant structure of the data.
So by forcing the data through these mathematical choke points, the machine develops a highly specific capability. It stops just memorizing inputs and actually begins to develop a capacity for imagination.
Yes. And this brings us to a really crucial division in machine learning tasks: discriminative versus generative modeling.
Okay, let's define those.
Broadly speaking, discriminative tasks are about drawing boundaries. You give the network data, and it draws a mathematical line separating the cats from the dogs. It discriminates.
Which has historically been the domain of supervised learning, right? Because those boundaries are defined by human labels.
Exactly. Generative tasks, however, are about modeling the entire distribution of the data so you can imagine or create new examples that fit the pattern. And generative tasks lean heavily on unsupervised learning.
I do want to push back on that strict separation, though, because the source material points out that this boundary is actually incredibly messy.
Oh, it's very hazy.
Yeah, there's a fascinating historical pendulum swing outlined in the text regarding image recognition. It started off heavily supervised. Then in the early days of deep learning, it became a hybrid.
Right, because engineers realized that deep supervised networks were just failing to learn. Their mathematical gradients would vanish before the network could train.
The vanishing gradient problem. So they used unsupervised pre-training to get the neural network's weights warmed up and oriented, and only then applied the supervised labels.
That was the standard protocol for a while. The unsupervised phase let the network map the underlying topology of the data before it had to worry about what things were actually called.
But then the pendulum swung all the way back. The text notes that strict supervision dominated again with the advent of specific mathematical tools, things like dropout, real U activation functions, and adaptive learning rates. So why did those specific tools suddenly make unsupervised pre-training obsolete for recognition tasks? I mean, why the swing?
It really comes down to solving the mechanical failures of early networks. You mentioned the vanishing gradient problem, where the learning signal fades away before reaching the deeper layers. Well, the real U activation function solved this.
Oh, so?
Instead of squashing signals into a tiny curve, real U simply lets any positive signal pass through cleanly. It maintains the mathematical momentum.
Oh, interesting. And what about dropout?
Dropout solved a completely different problem: co-adaptation. By randomly severing connections between neurons during training, dropout forces the network to build redundant, robust pathways rather than just relying on a few fragile connections.
Ah, I see.
Once those mechanical roadblocks were cleared, pure supervised learning was suddenly incredibly efficient for discriminative tasks.
So the math finally caught up.
Yeah.
And they just didn't need the unsupervised warm-up act anymore for drawing those boundaries.
Exactly.
But as you mentioned, for generative tasks, where the machine actually has to imagine, unsupervised learning remain king, and the mechanism for how it learns to imagine is brilliant. It uses masking.
Yes. Denoising autoencoders and architectures like BERT are prime examples of this.
Think about it like this. Imagine you're given a massive, complex jigsaw puzzle, but someone has randomly stolen 10% of the pieces.
And you don't have the picture on the box to guide you.
Exactly. You have to look at the shapes and colors of the pieces surrounding the holes to deduce exactly what the missing pieces must look like. That's what these models are doing. You feed them a sentence from the wild internet, you deliberately mask out a word, and you force the model to calculate the probability distribution of the entire human vocabulary to infer what belongs in that blank space.
And by repeatedly solving billions of those masked puzzles, the network isn't just memorizing vocabulary.
Right.
It is mapping the deep, latent relationships of human syntax, context, and logic. Once it possesses that generative structural map, it becomes a foundational model.
So you take that massive unsupervised brain, apply a tiny bit of supervised fine-tuning, and it can perform specific downstream tasks, like sentiment analysis or text classification.
Precisely.
But here's where it gets really interesting. If there is no teacher grading those billions of fill-in-the-blank puzzles, how does the machine internally correct its weights when it guesses wrong?
That's the million-dollar question.
And early researchers didn't look at traditional computer logic to solve this. They looked directly at the laws of physics.
They turned to thermodynamics, specifically the concept of an energy function.
Okay, break that down for us.
When an unsupervised network makes an error, when its internal representation fails to accurately mimic the data distribution, the system doesn't register a simple Boolean false. It registers that error mathematically as an unstable, high-energy state.
So let's visualize that.
Hmm.
I know a lot of people use the metaphor of a ball perched on a hill, wanting to roll down to a valley. But I think a better way to grasp this is to imagine a highly tense, vibrating guitar string.
Yeah, I like that.
When you pluck it randomly, the vibration is chaotic, dissonant, full of high physical energy. But over time, the physical constraints of the string force it to settle into its natural, resonant harmonic frequency. The chaos dissipates into stability.
That is a much more accurate representation of the math, especially since the source material explicitly mentions Paul Smolinski's concept here. Smolinski proposed that the negative of this energy state should literally be called harmony.
Harmony. That's almost poetic.
It is. An unsupervised network actively updates its internal weights to seek out the lowest possible energy state, which maximizes its internal harmony with the data.
And the history of this is just wild. The text points to John Hopfield in 1982. He didn't build his network based on brains. He based it on the physics of magnetic domains in iron.
Yes, the Hopfield network.
He treated artificial neurons like binary magnetic moments, atoms, with spins that can only point strictly up or down.
The mechanical genius of Hopfield's design was using symmetric connections. If neuron A connects to neuron B with a certain weight, neuron B connects back to neuron A with the exact same weight.
And this symmetry is what allows the entire network to be described by a single global energy equation.
Exactly.
And it resulted in what the text calls content addressable memory. If you give the network a noisy, corrupted piece of data like half of an image it's seen before, the network spins its magnetic neurons, flipping them up and down, vibrating like that guitar string, until it mathematically settles into the nearest low-energy state.
And that low-energy state happens to be the perfectly uncorrupted original memory.
It's incredible, and from there, the architecture evolved to incorporate Ludwig-Boltzmann's thermodynamics, bringing in hidden layers of neurons to represent more complex, unseen variables.
Creating the Boltzmann machine. However, the source material highlights a critical architectural fork in the road here. The transition to restricted Boltzmann machines, or RBMs.
Right, I was looking closely at that section. The restriction is very specific. It prohibits lateral connections, meaning neurons in the hidden layer are strictly forbidden from communicating with other neurons in the same hidden layer. If we think about this mechanically, if those neurons could talk to each other, you'd create an intractable echo chamber.
You absolutely would.
Every time one neuron updated, it would change the state of its neighbor, which would change the first neuron again. You'd never be able to calculate the overall energy state because the feedback loop would be infinitely recursive.
You've hit on the exact mathematical bottleneck. Calculating the normalizing constant for those probabilities, what physicists call the partition function, becomes exponentially impossible as the network grows.
So cutting those lateral connections fixes it.
Yes. By cutting them, the RBM creates a bipartite graph. The math suddenly becomes conditionally independent. Given the state of the visible input neurons, you can perfectly calculate the probability of the hidden neurons in a single parallel step. It makes the thermodynamic search for harmony computationally tractable.
So on one side of the discipline, we had engineers wrestling with the heavy mathematics of thermodynamics and iron magnets. But the test reveals that simultaneously, other researchers were looking in a completely different direction to solve the unsupervised problem.
They looked at biology.
Because human brains cluster massive amounts of chaotic sensory data every single second, incredibly efficiently, without needing to calculate a partition function.
They pivoted from physics to neuroscience. They anchored their work in Donald Hebb's biological principle from 1949. Neurons that fire together wire together.
Such an elegant phrase, but the mechanics behind it are profound. Hebbian learning dictates that the synaptic connection between two neurons is strengthened exclusively based on the coincidence of their firing.
There's no central supervisor in the brain evaluating the accuracy of the thought.
Right. It's like creating a well-worn path in a park. The connection is reinforced simply by the coincidence of people walking it at the same time, without a park ranger, a supervisor directing them. It completely ignores error rates.
And the source material highlights an even more precise mechanical evolution of this called spike timing dependent plasticity, or STDP.
Which moves beyond simple coincidences, right?
Exactly. It looks at the exact millisecond timing of the action potentials. If neuron A spikes just a few milliseconds before neuron B, the synapse strengthens. It encodes causality.
Wow.
But if neuron B spikes without neuron A, the connection weakens.
So it's physically etching a map of cause and effect into the network, based purely on the temporal rhythm of the data passing through it.
Mm.
And this biological mimicry led to completely different unsupervised architectures, specifically self-organizing maps, or SO, and adaptive resonance theory, RT.
Let's examine the mechanics of those. A self-organizing map approaches clustering spatially. It takes highly complex multidimensional data and forces it onto a two-dimensional topological grid.
Okay, so it's making a map.
Literally. As the network trains, it mathematically pulls neurons that respond to similar inputs closer together on that grid. It builds a physical map where, for example, the concept of apple ends up spatially located right next to pear.
It's organizing the chaos geographically. But what about adaptive resonance theory? The text suggests RT solves a very specific cognitive issue called the plasticity-stability dilemma,
Right.
which, if I'm understanding the mechanism correctly, is the problem of how a network learns a completely new pattern without catastrophically overwriting everything it has already learned.
That is the exact dilemma. If a network is too plastic, it forgets its past. If it is too stable, it can't adapt to new information.
It just stubbornly sticks to what it knows.
Exactly. RT solves this dynamically, allowing the network to continually create new clusters for new data on the fly. And it governs this process using a mechanism called the vigilance parameter.
The vigilance parameter. Let's
Yeah.
dig into how that actually functions. It acts like a threshold for similarity, right?
Correct. When new data comes in, it resonates with the existing clusters. If the vigilance parameter is set high, the network is acting hypercritical. The new data must be a near-perfect mathematical match to an existing cluster to be grouped with it.
If it isn't,
If it falls even slightly short of that high threshold, the network instantly creates a brand new, distinct cluster.
so high vigilance gives you a massive number of very specific, highly granular categories. The source notes this is critical for tasks where the margin of error is zero, like radar analysis or automatic target recognition.
You don't want the network lumping a civilian aircraft and a fighter jet into the same generic flying object cluster.
Definitely not. And conversely, if you lower the vigilance parameter, the network accepts broader similarities, grouping things into a few overarching categories. It gives the engineer precise mechanical control over how the machine perceives the granularity of the world.
If we connect all of this to the bigger picture, whether we're utilizing the spatial topology of SMs, the biological timing of STDP, or the thermodynamic energy functions of restricted Boltzmann machines, the ultimate objective of unsupervised learning fundamentally comes down to statistics.
Right.
It's the field of density estimation.
So moving from the architecture to the underlying math.
Yes. Unsupervised learning is not calculating conditional probabilities based on labels. It is attempting to infer an a priori probability distribution from the raw noise. It wants to discover the hidden, unobserved variables that are actively generating the data we see.
And the text highlights latent variable models to explain this, specifically using topic modeling as a practical mechanism. Like, imagine you're analyzing millions of unstructured legal documents. The machine constantly sees the words tort, liability, and damages clustering together. The machine has no conceptual understanding of human law.
Learn it all.
But the math identifies a latent variable, like an invisible gravitational center, that is causing those specific words to co-occur. It isolates the hidden topic.
Finding that hidden topic is the goal. But the mathematical mechanism you use to discover those hidden parameters is heavily debated in the literature, which brings us to a crucial comparison in the text. The expectation maximization algorithm, or EM, versus the method of moments.
This is where I really want to push on the math, because the text dedicates significant space to both. It introduces EM as a highly practical, standard method for estimating these latent variables.
It is very standard.
It works iteratively, right? It guesses the hidden parameters, calculates the expected likelihood of the data based on that guess, updates the parameters to maximize that likelihood, and repeats. But if EM is so standard and practical, why does the source pivot so heavily into the method of moments? What is the mechanical flaw in EM?
The fatal flaw in EM is that it navigates the mathematical landscape blindly. Because it relies on iterative guessing, it is notoriously prone to getting trapped in what mathematicians call local optima.
Okay, let's visualize that mathematical landscape. Imagine you are trying to find the highest peak in a massive, rugged mountain range.
Yeah.
But you are completely blindfolded.
Good luck with that.
Right. Your only strategy is to take a step in whatever direction feels like an upward slope. You will eventually reach a peak and stop because every step around you goes down. But you might just be standing on a tiny foothill, completely unaware that Mount Everest is 10 miles away. That's the local optimum trap.
That is a perfect structural analogy. EM gets stuck on the foothill and mathematically declares it has found the true underlying parameters of the universe. It provides absolutely no guarantee of finding the global truth. The method of moments was resurrected in modern machine learning specifically to bypass that blindfolded climbing.
So how does the method of moments guarantee it finds the actual summit without, stepping through the landscape?
By relying on the fundamental structural statistics of the entire data set at once. It uses empirical samples, the moments of the random variables.
Like the first order moment.
Exactly. The first order moment is simply the mean vector, the average center of the data. The second order moment is the covariance matrix, which maps exactly how every single feature in the data set varies in relation to every other feature.
So it's not guessing a path. It's taking a massive structural snapshot of the entire data distribution.
Yes. And it extends this to third order and higher order tensors.
A tensor is essentially a multidimensional matrix, right?
Right. By calculating the tensor decomposition, mapping the complex multidimensional skew and shape of the data, you can mathematically reverse engineer the exact, true global parameters of the hidden variables. You don't guess and check. You calculate the structural geometry of the data, and the math guarantees you land on the global optimum.
Wow. It is a vastly more robust mathematical mechanism, completely immune to the deceptive foothills of the data landscape.
It really is.
So what does this all mean? We started this deep dive by looking at machines dropped into the wild, crawling billions of chaotic web pages without a single human label to guide them.
And we've seen the incredible mechanical ingenuity required for them to survive and map that wilderness.
Yeah, they reduce the dimensions of reality down to its principal components. They play generative games of fill in the blank to map the structural grammar of our world.
They mimic the physical thermodynamics of tense, vibrating systems seeking mathematical harmony.
They leverage the biological timing of firing neurons, and they apply the rigorous multidimensional tensor math of the method of moments to definitively lock on to the hidden truths driving the noise.
It is a profound synthesis of physics, biology, and advanced statistics, all dedicated to the single goal of finding order in the void.
It truly is a masterclass in architectural problem solving. But, tracking this evolution leaves me with one final, slightly haunting thought. Something for you to mull over as you observe the current trajectory of artificial intelligence.
Oh.
The foundational premise of everything we've discussed is that unsupervised learning infers an a priori probability distribution of reality, strictly from the raw data harvested in the wild. It learns what the world is based on the unfiltered exhaust of human digital existence.
It assumes the data it digests is a faithful representation of the underlying reality.
Exactly. So we have to ask, what happens to the internal architecture of these models a few years from now? We are rapidly approaching a point where the vast majority of the text, images, and code in the wild on the internet will not be human at all.
Right, it will be synthetic data.
Generated by other unsupervised models. If these algorithms learn the rules of the universe purely by mapping their environment, and that environment becomes an entirely artificial construct, what hidden latent variables will they find then?
That's a chilling thought.
Will they suffer a total model collapse? Or will they achieve a strange, highly stable new harmony that is completely and fundamentally detached from human reality?
When the feral machines begin learning exclusively from the artifacts of other machines, the underlying mathematics of what constitutes truth will fundamentally change.
Like a cartographer painstakingly mapping a continent, only to realize the landmass was entirely engineered by the previous surveyor. Thank you for joining us on this deep dive. We will see you next time.